All right, one more week to go. Are we ready for week 7? Hi, everybody. I'm in my back room this time. I'm working in the evening, so it looks a little bit more dramatic back here. All right. In week 7, I'm going to present a little bit of a week 7 overview. The theme of the week is problems with two or more random variables. So for most of this course, we've been working with problems that have only one random variable, such as number of children or proportion of tennis calls, tennis challenges that were overturned. Um, in week 6, we did take a look at comparing two different populations, such as a population of male players and a population of female players, and then comparing one random variable to see how it differs between them. We looked at differences of means and differences of proportions. So this in week 7, it's very much related to what we did in week 6, but it's a little bit broader and it goes off in different directions. So, for example, in that example we did with comparing rates of tennis calls between male and female players, you could kind of think about the male and female as being another random variable, like gender. So that's a qualitative variable, obviously. But the material in week 7 is going to allow us to study two different random variables that might both be quantitative. For example, number of children and monthly expenditures on groceries. And what we're going to be interested in primarily is how two or more variables like that affect one another, or might depend on each other, or even allow us to make predictions about each other. So it's a very important topic. Now, as far as our testing on it, we have a pretty big homework set this week. There are something like, I think there's 26 or 27 homework problems. But the good news is that this material is only lightly tested afterward. You're going to have a quiz in week 7, quiz 3. That will cover the material that we saw in weeks 5 and 6. So week 7 will not be on any future quiz. And then, of course, the only assignment after that is the final exam. And I suppose this material covers about 1/7 of the final exam, which makes sense. There are something like 3 problems out of 20 that are related to this. All right, so let's start out. This book, again, like it does sometimes, this course kind of jumps around from one different point of the textbook to another. We start out with section 2.4, oddly enough, and then make some leaps into chapters 10 and 11. As it turns out, section 2.4 is the most heavily tested section of this week. It's called Scatterplots and Correlation, and it's a pretty basic section. It really is just going to be laying down the fundamental concepts that we'll need for the rest of this discussion. Those concepts being the scatterplot and linear correlation, and then finally the question of determining whether that correlation is significant. So let's start out with the concept of the scatterplot. A scatterplot is a representation of data with two random variables, the theme of the week, which we will normally abbreviate as X and Y. Now, so let's illustrate that by looking at our examples page. So as usual, my posts, the files that I'm posting along with this announcement this week will contain that lecture outline as well as a page or a packet for illustrations and examples. Okay, so for section 2.4, illustrations and examples, we start out by constructing a scatterplot. A large corporation is auditing 9 of its call centers across the U.S. It makes a list of the number of customer service representatives on duty that day, which we'll call X, and the average hold time per customer call, which we will call Y. The results are displayed in the table. So in this column, we have a list of all the call centers. In this column, we have a list of how many representatives are working at each call center, variable X. And then in this column, we measure the average hold time for each call that's handled by that call center, measured in minutes. And we'll call that variable Y. So for example, at the Alabama call center, there are 32 representatives taking calls, and the average hold time is 5.8 minutes. I have that data in StatCrunch over here. Scratch that thought. Before I go to StatCrunch, I want to illustrate what this looks like as a scatter plot. So you remember from high school plotting points. So if we have a point with coordinates x equals 32 and y equals 5.8, and then if we come down here to the graph paper, x equals, I forgot what it was already, x equals 32, y equals 5.8, so that would actually give us this point here. So this point represents that Alabama call center. I've highlighted Hawaii as an example. So if we plot the point 27, 12.9, x equals 27 representatives, y equals 12.9 minutes. So each point on the scatter plot represents, in this case, one call center. And as usual, I really emphasize the connections, all these different connections that we need to make between language, tables, graphs, variables. Those connections are what it's all about. So when you look at a scatter plot, I want you to always make that connection that each point can be summarized by one sentence about one element from this population or sample. Okay, so this dot is Hawaii, this dot is Alabama, and again, each one of those dots tells you a sentence, how many representatives it has, and how long the calls are holding. Okay, so now let's go to StatCrunch because we need to learn how to actually generate this graph. Here's the same data copied and pasted into StatCrunch. And it's probably not going to be too much of a surprise. I think you could probably stumble upon this on your own. If we go to Graph, one of the options here is Scatterplot. Okay. He's going to ask us for the variables. The X variable in this case is located in the reps column. The Y variable is located in the hold time column. Those columns are not always labeled. So they usually just by default say variable 1, variable 2, variable 3. But I like to give them names. Okay, and then if we click Compute, lo and behold, there is our scatter plot. That's how I obtained the scatter plot for your handout. I just copied this one. After we graph a scatter plot, the next thing that we'll want to be concerned about is looking for patterns that these points exhibit. So if we return to the lecture outline, there are three main patterns that we want to be aware of. The most important one is the straight line pattern. If the points seem to more or less follow a straight line, we call that a linear correlation between x and y. And what that basically means is that while x grows, y grows or shrinks proportionally to that. It's a very interesting pattern and a simple pattern, so it's an important one to look for. Another kind of pattern that we might see is basically sheer randomness. I sometimes call this a cloud or maybe a shotgun pattern. And that would indicate that there is no correlation between x and y. And then third, we might also sometimes notice that there's some kind of a curved nonlinear pattern. Let's go to the examples and illustrations sheet to look at some of these. Okay, so this is an obvious example of data with a very strong linear pattern. All the points just happen to fall on a straight line here. They're not usually that strong, and we'll come back to that topic soon. This is what I mean by the cloud or shotgun pattern. And another way of thinking about this is that there are basically points in every quadrant of this graph. Upper right, upper left, and lower right. So while x is growing, y is just literally still all over the place. Here are a couple of other examples of straight line patterns that we're going to study in a moment. And then here's a very clear nonlinear curved pattern. So those are the qualitative shapes of correlation. Of course, in this class, we're always interested in quantifying things. So correlation can actually be, let me emphasize that this means linear correlation. Linear correlation can be quantified with a variable that we call the coefficient of linear correlation, and it's abbreviated with the letter R. I'm not sure exactly why. That might stand for the word regression. Or maybe it stands for relation. The word correlation literally means co-relation, right? It means two variables that are related together. All right, so the strength of the linear correlation is measured with this variable R, which ranges from -1 to +1. And theoretically, it could be a -1 and it could be +1. So it can be either positive or negative, and it can either be close to 0 or close to 1, or somewhere in between. So what do these different numbers mean? If R equals 1, that means a perfect fit on a straight line, and the variables increase together. As R shrinks a little bit, that means that the points will fall moderately close to a straight line, but still increase together. R equals 0 describes that cloud pattern with no correlation. And then when R becomes negative, we see the same kinds of patterns. For example, if R is negative 0.5, the points again fall moderately close to a straight line. But this time, Y decreases as X increases. So you're going to have a downward slope. And then, of course, at the very bottom limit, R would be -1 if we see a perfect fit on a straight line with a negative slope. In this section, by the way, R would be given to us. We don't have to calculate it just yet. But let's go back to these examples. So this graph is an example when R equals +1. Again, that means that there is a perfect positive linear correlation between X and Y. And that basically never happens in empirical data. You're never going to take a sample that's that perfect. So it really only happens in a theoretical sense. And the example that I've concocted here is if you have a thermometer that is measuring temperature in Fahrenheit and simultaneously on the Celsius scale, well, there's actually an equation that relates these two numbers to each other. It's a linear equation. So there's a mathematical reason that those points would fall together in a straight line. So, for example, when Fahrenheit says 10, Celsius says -12.2. That corresponds to this point here. And if we plotted all those points, well, it's not a surprise that they fall perfectly in a straight line because that's the definition of Celsius. It's a formula for related to Fahrenheit. Now, in this example, I plotted 50 points, actually. I only copied and pasted 10 of them here, representing students at a school. Each student has an ID number and a GPA. And you would probably expect that GPAs are not related to ID number. And that's exactly what we see in this pattern, a cloud pattern. These graphs are what most scatterplots actually look like, an intermediate correlation. So here are a few points that have a correlation of 0.5. So as you can see, they generally trend upward to the right, but they're pretty loosely fit around that line. This graph has an R coefficient of -0.8. So you can see that the downward to the right trend is pretty strong for this one. And because it's going down to the right, that's why R is negative. Now, just one other thing to be aware of with a nonlinear correlation. A graph like this could have a low value of R because it's nonlinear, even though there's a very strong pattern to it. So just remember that R, it only measures the strength of the linear correlation, not any other curve.